Welcome back to the deep dive. You know how we love to take those concepts that often sound like pure science fiction and really dig into their rigorous scientific and philosophical foundations.
Absolutely. Getting past the surface level.
Exactly. Well, today we're tackling an idea that truly bends the mind. I mean, it challenges our everyday understanding of existence itself, the multiverse hypothesis.
It's a big one.
Oh, yeah. And we're moving far beyond, the pop culture stuff you see in movies or comic books. We want to understand why scientists are even seriously considering multiple universes, what that actually means,
Mm-hmm.
and, maybe most importantly, why it matters to you.
Mm-hmm.
Our guide today is here to help us make sense of it all. We'll be drawing especially from insights like those in works exploring the quantum enigma and the scientific basis for the multiverse. This isn't just about cool ideas. It's really about pushing the very boundaries of what we understand about reality.
It really is a journey into the deepest questions. And what's immediately striking, I think, about the multiverse is that it isn't just one single monolithic idea.
Right, not just parallel worlds like in the movies.
Not at all. It's more like a diverse family of distinct theoretical models. And each one actually arises from different really crucial problems and paradoxes within modern physics, whether it's the weirdness of quantum particles or the huge sweep of cosmic evolution.
Okay, so different problems, different multiverse ideas.
Precisely. Understanding that distinction is absolutely key to grasping its true complexity. And, in its very essence, the whole multiverse concept forces us to reconsider the nature of scientific inquiry itself. It challenges our preconceived notions of what even constitutes a universe and, well, how we observe it.
Okay, so to really appreciate where we are today with the multiverse, we actually have to start, well, not in a modern physics lab with super colliders, surprisingly.
And, well, much further back.
Yeah, thousands of years ago, really, in the cradles of ancient thought. And this is where the story gets really fascinating, I think, because the philosophical seeds of this idea were planted by some of humanity's earliest thinkers. Take the Greek atomists, for instance. Philosophers like Leucippus and his student Democritus. They were around the 5th century BC.
Right. Pre-Socratics.
Exactly. Their cosmology was built on this remarkably simple yet, well, profoundly expansive idea. They believed in an infinite void, just endless empty space, filled with an infinite number of tiny, indivisible particles they called atoms.
Original atoms, yeah.
Uncuttable things.
Right. And these atoms, they figured, were just in constant random motion, bouncing around, colliding, vibrating.
That's right, a cosmic chaos.
And from this chaotic dance, they thought it was just inevitable, given infinite time and infinite space, that these atoms would arrange themselves in every possible way.
Just probability, really. And that, in turn, would lead to the spontaneous formation of, well, an infinite number of worlds. They literally pictured a spatially distributed multiverse.
Worlds spread out in space.
Exactly. Countless other Earths, maybe with their own suns and stars, far beyond anything we could see, just popping into existence because of random atomic combinations in this endless void.
It's an astonishing leap of, well, philosophical deduction, made without any telescopes or quantum mechanics, obviously.
It really is just pure thought.
And that basic idea, the idea of countless worlds, it really continued to evolve. If we broaden our perspective just a bit, we see another really compelling vision from the Stoics, thinkers like Chrysippus, who came a few centuries after Democritus.
Okay, so how did their idea differ?
Well, they offered a contrasting but maybe equally profound vision. Their multiverse wasn't so much spread across infinite space, but across infinite time.
Ah, interesting. A temporal multiverse.
Kind of, yeah. Their core belief was that the cosmos goes through these eternal cycles, destruction and regeneration.
Like a phoenix universe.
Exactly. The world would eternally perish in this grand conflagration, a fiery end, only to be reborn and regenerated, starting its existence all over again.
Okay.
And each of these cycles, in essence, created a new universe, a multitude of universes unfolding throughout this infinite repeating cosmic drama. And what's truly remarkable is that some Stoics even believed that in each new cycle, events would repeat exactly as they had before.
Wow. So infinite identical worlds, one after another.
Yeah.
With identical lives.
That was the idea for some, yeah. It's just incredible to think that these ancient minds, millennia ago, were grappling with concepts of infinite worlds, cosmic cycles, the nature of repetition, things that still echo in physics and philosophy today.
It really shows how deep this quest goes, doesn't it? This need to understand what's beyond our immediate world.
It seems fundamental to human thought.
And this quest wasn't just abstract philosophy, right? It started to get tangled up with theology, too.
Absolutely. Stepping forward in time, this idea of a plurality of worlds resurfaced quite significantly within the Roman Catholic Church. This spurred major debate, especially in the 13th and 14th centuries.
What was the debate about?
The core question was whether God, being omnipotent, could create other Earth-like worlds, maybe even inhabited ones, within our existing universe. Could he have made more than one?
So a question of God's power and choices.
Exactly. And this wasn't just idle speculation. It actually led to a pretty pivotal moment in 1277. The Bishop of Paris, Etienne Tempier, acting with papal authority, issued this decree condemning 219 philosophical and theological propositions, things thought to be heretical or dangerous.
Right.
And among these condemnations was the specific idea that the first cause, God cannot make many worlds.
Wait, so they condemned the idea that God couldn't make many worlds.
Precisely. It's a bit paradoxical, isn't it? By condemning the negation, by saying it's wrong to claim God can't make many worlds, the Church implicitly affirmed that God could indeed make many worlds if he chose to.
Ah, clever. So it actually opened the door for more thinking about it.
That's the effect it had, yeah. It intellectually freed thinkers from the constraint of assuming a single, unique creation. And this shift then helped pave the way for, well, more radical thinkers later on.
Like Giordano Bruno.
Exactly like Giordano Bruno in the 16th century. He took this idea and ran with it, way beyond just other Earths. He argued our sun wasn't special.
Just another star.
Just one of an infinite number of stars, he claimed. And each of those stars, he thought, was potentially circled by life-bearing planets, all existing within an infinite universe. His vision was truly boundless.
From possible other worlds to an infinitely populated cosmos. That's a huge leap.
It was. And famously for this and other unconventional views challenging church doctrine, Bruno was ultimately tried for heresy and burned at the stake, a tragic end for such a bold thinker.
Definitely. And speaking of the words we use, the term multiverse itself, where did that actually come from? It sounds modern.
You'd think so, but its origin is quite surprising and actually not cosmological at all initially.
Really?
Yeah, it was introduced much later, 1895, by the influential American philosopher William James.
William James, the pragmatist psychologist.
That's the one. But he wasn't talking about physics. He described nature as a moral multiverse, not a moral universe.
A moral multiverse. What did he mean by that?
Well, James was really interested in the inherent messiness, the chaos, the disunity, what he called the plasticity of the natural world, how it's always changing, unpredictable, multifaceted.
Okay.
He felt the idea of a single, perfectly ordered, coherent, moral universe was just too simple. It didn't capture the messy, often contradictory reality of, human experience and nature itself. So his term highlighted the diverse, pluralistic, sometimes chaotic aspects of reality more from a subjective, experiential viewpoint.
So his philosophical use, even though it wasn't about parallel physical universes, sort of laid some groundwork.
I think you could argue that, yeah. It got thinkers used to the idea of a reality that isn't necessarily singular or perfectly unified, but maybe diverse, maybe fragmented.
And that made it easier, maybe, for the term to be adopted later in physics.
Potentially. It became a useful label when physicists needed a concept to tackle these really fundamental scientific problems they were encountering in the 20th century.
Right. So the big takeaway here is that the multiverse hypothesis isn't just some modern scientific fad pulled out of thin air.
Not at all.
It's really a continuation of this centuries-old human quest, a deep, enduring inquiry into the sheer scale of our existence and, well, the apparent strangeness or fine-tuning of our own reality.
It's a testament to our enduring curiosity, constantly being reshaped by new tools and new perspectives, from philosophy to theology to physics.
Which brings us to modern physics. And how do we bridge that gap? Why did this ancient idea suddenly gain such urgency now?
That bridge is absolutely crucial, because we now face these profound, unavoidable paradoxes that come directly from the two pillars of modern physics: general relativity and quantum mechanics.
Einstein's theory of gravity and the theory of the very small.
Exactly. General relativity is fantastic for describing the big stuff stars, galaxies, the cosmos. Gravity as curved space-time. Quantum mechanics governs the tiny stuff, the subatomic world, particles, weird quantum behavior.
And both theories work incredibly well in their own domains, right?
Astonishingly well. They make incredibly precise predictions that have been verified again and again, but They are fundamentally incompatible.
They don't play nice together.
They really don't. They use different mathematical languages. They have different underlying assumptions about reality. We don't have a single unified theory that seamlessly connects them, a theory of everything.
The holy grail of physics.
Pretty much.
Yeah.
And the multiverse concept, speculative as it might be in some forms, offers a potential path towards reconciling them. Or, at the very least, it offers a compelling explanation for some of the most puzzling, almost improbable features of our reality that these theories throw up. Features we need to unpack.
Okay, so let's zoom right in on one of those critical problems then. Let's dive into probably the most baffling, persistent riddle in modern physics. It's an enigma right at the core of reality. The quantum measurement problem.
This is where intuition really starts to fail us.
Totally. Okay, so at the heart of quantum mechanics is this concept called superposition. So imagine a quantum system, right? Like an electron or a photon. Quantum theory says that before you measure it, it doesn't exist in just one definite state. It exists in a combination of multiple possible states simultaneously.
All possibilities existing at once, in some sense.
Yeah, it's like it's in multiple places at once, or spinning both ways at the same time, or being both a particle and a wave.
It's inherently fuzzy.
Right. And the main equation of quantum mechanics, the Schrödinger equation, actually describes how this fuzzy state evolves over time. And that evolution is perfectly deterministic and linear. Everything seems smooth and predictable at the quantum level.
The math works beautifully for describing that evolution.
But here's the giant contradiction. The measurement problem. When we actually measure the quantum system, what do we find?
Always a single definite state.
Always. We never see the superposition directly in our everyday world.
Right.
We don't see an electron in two places. We don't see a cat that's both dead and alive. Spoiler alert.
Yes. We'll get to the cat.
So the quantum measurement problem is exactly this. How and why does that indefinite superposition suddenly resolve into one single concrete outcome the moment we look at it?
What makes reality choose?
Yeah. And maybe even weirder, what is measurement? What physically counts as an observation that forces this choice? Is it a Geiger counter? Is it a human eye? Is it consciousness? It's a question that's haunted physics for nearly a century.
It really has. And to truly illustrate this bizarre paradox and its implications, nothing beats Schrödinger's cat. It's probably the most famous thought experiment in physics.
Lay it on us, the poor cat.
Okay, so imagine, purely hypothetically, of course, a cat sealed inside an opaque steel box, completely cut off from observation.
Got it. Cat in a box.
Inside the box with the cat is a rather diabolical device. There's a single radioactive atom. And this atom has exactly a 50% chance of decaying within 1 hour.
50-50, like a coin flip.
Exactly. If the atom does decay, it triggers a Geiger counter. The counter then releases a hammer, which smashes a vial of poison gas.
And the cat dies.
Right. But if the atom doesn't decay in that hour...
The mechanism doesn't trigger, the cat lives.
Precisely. Now, here's the quantum weirdness. According to the principles of quantum mechanics, until the box is open and the atom's state is measured, that atom exists in a superposition. It's both decayed and not decayed simultaneously.
Okay, the atom is fuzzy.
But the cat's fate is directly linked and tangled with the atom's state. So the entire system inside the box atom, trigger, cat, gets locked into this bizarre superposition.
So the cat is what?
The cat itself is in a superposition of decayed atom dead cat and intact atom live cat. According to the math, it's literally both dead and alive at the same time.
That just feels wrong. I mean, intuitively.
It absolutely does, and that's the point. Because when we, the observers, finally open the box, what do we find?
A dead cat or our alive cat. Never both.
Never both. Always one definite outcome. So the central puzzle is, what did the act of opening the box, of observing the system, do? How did it force that fuzzy quantum state into a stark classical reality of either life or death?
What broke the superposition?
Exactly. What constitutes the measurement that resolves the ambiguity? That's the measurement problem made flesh. Or, well, fur.
So, yeah, this is a profound problem. What does this actually mean for how reality works? For almost 100 years now, physicists have been wrestling with this, and it's led to very different ways of thinking about quantum mechanics, different interpretations.
Interpretations trying to make sense of the math and the observation.
Right. The oldest and probably still most famous one is the Copenhagen interpretation, championed by giants like Niels Bohr and Werner Heisenberg back in the 1920s.
The standard view for a long time.
Yeah. And its core idea is pretty radical. It says quantum mechanics is intrinsically indeterministic, fundamentally random.
Meaning the randomness isn't just because we don't know enough, it's inherent in nature.
Exactly. Before you make a measurement, properties like position or spin don't even exist in a definite sense. There's no hidden reality to uncover. The system just is in that superposition.
It's a statement about what can be known, almost.
Kind of.
Yeah.
And instead of predicting what will happen, the theory gives us the Born rule. This is a key part. It just tells you the probabilities of getting specific outcomes if you make a measurement.
So 50% chance the cat is alive, 50% dead, according to the Born rule. But it doesn't say why you get one or the other.
Right. It just gives the odds. And the mechanism Copenhagen proposes is wave function collapse.
The infamous collapse.
Yeah. It states that at the exact moment of measurement, whatever that is, the system instantaneously and irreversibly collapses from its superposition into just one single definite state. Poof. All the other possibilities just vanish.
Gone. Wiped from reality.
But here's where the critics jump in. Copenhagen is often slammed for being, well, imprecise. Vague, even.
It leaves big questions unanswered.
Totally. It doesn't explain what actually causes the collapse. It doesn't define the boundary between a quantum system and a classical measuring device. Where does quantum end and classical begin?
The shifty split, as John Bell called it.
Right. And it seems to give a special, almost mystical role to the observer or the measurement act itself, which many physicists find deeply unsatisfying. It feels incomplete, maybe even ad hoc, like a rule bolted on just to match observations, not derived from deeper principles.
It works incredibly well for calculations for predicting experimental results. But as a fundamental description of reality, many feel it falls short.
So what are the alternatives, if Copenhagen isn't the whole story?
Well, one major alternative, taking completely different tack, is the Broglie-Bohm theory. You might also hear it called pilot wave theory.
Okay, de Broglie-Bohm, how does that work?
It was first suggested by Louis de Broglie in the 1920s, then fully developed by David Bohm in the 1950s. And unlike Copenhagen, this theory is fully deterministic, no fundamental randomness. And crucially, it completely avoids wave function collapse.
No collapse. How does it manage that?
Yeah.
And deterministic.
Yeah. The premise is actually quite elegant in a way. It says particles, like electrons, always have definite positions and definite momenta. Always, regardless of whether we measure them or not.
So no fuzziness. The electron is always somewhere specific.
That's it. The fuzziness we associate with quantum mechanics, in this view, comes from the wave function. But here, the wave function isn't the complete description of the particle. Instead, it acts like a guiding wave or a pilot wave.
Guiding the particle where to go.
Precisely. It directs the motion of the particle, which always has a real, definite position. It's just that we might not know that position until we measure it.
Okay, so if the particle always has a definite state, how does that solve the measurement problem?
Well, very simply, it says there is no measurement problem. Because the physical variables, like position, always had a specific value. There's no superposition of states that needs to mysteriously collapse into one outcome.
It was always definite. We just didn't know which state it was in.
Essentially, yes. The measurement simply reveals the pre-existing reality. So this approach is often called a quantum theory without observers because the observer plays no special role. The whole universe, including us, is just one big deterministic system evolving according to these guiding waves.
But deterministic. That sounds counter to the randomness we see in quantum experiments.
It does. The apparent randomness in Bohm's theory comes from our ignorance of the particle's precise initial position within the wave packet. If we knew the exact starting point, we could predict the outcome deterministically. But we can't know it with perfect accuracy.
Okay. Are there downsides to this? Sounds quite neat.
There are challenges. The biggest one is non-locality. The guiding wave can instantaneously influence particles across vast distances.
Faster than light.
Spooky action at a distance. Kind of. It doesn't let you send information faster than light, so it doesn't violate relativity in that sense. But it does imply a deep, instantaneous connection between distant parts of a system, which many physicists find uncomfortable. It paints a very different picture of reality deterministic, guided by these waves, and deeply interconnected in a non-local way.
So we had this fundamental split then. Copenhagen says reality is fundamentally random. Collapse is real but unexplained. De Broglie-Bohm says reality is deterministic. Particles are always real, guided by waves, but involves non-locality.
That's a good summary of the dichotomy. It really gets to the heart of the quantum enigma. Is the universe inherently probabilistic, or is it deterministic in a way that's hidden from us?
Copenhagen works pragmatically but leaves those deep philosophical questions hanging.
Right. While alternatives like de Broglie-Bohm and the many-worlds interpretation we're about to discuss try to offer a more coherent, internally consistent picture without invoking a mysterious collapse or a special role for observers. But they come with their own conceptual baggage like non-locality or, well, countless other universes.
It really raises this crucial question about what we expect from a physical theory. Just accurate predictions or a satisfying picture of reality itself.
That's the ongoing debate.
That is a powerful question.
Right.
And it leads us right into maybe the most radical, some would say elegant, solution to this whole quantum enigma, the many worlds interpretation, MWI.
Brace yourself.
Yeah, prepare yourself, because this is where it gets really mind-bending. This is the one that seriously makes you question what reality even means. It was first proposed by this brilliant physicist, Hugh Everett III, who was initially kind of overlooked.
His PhD thesis in 1957 didn't make a huge splash initially.
Right. But his idea fundamentally changes the game regarding quantum measurement. The central idea, the core principle, is this. The universal wave function, the mathematical object describing the entire universe, is objectively real. And crucially, unlike Copenhagen, it never collapses.
A collapse ever.
Never. The evolution of reality as a whole, Everett said, is rigidly deterministic, according to the Schrödinger equation, and it's local. No spooky action. Everything that can happen, according to the wave function, simply does happen.
Okay, hold on. If there's no collapse, how do we end up with definite outcomes? Why does the cat look either dead or are alive?
Because instead of collapsing possibilities away, MWI says that every quantum event with multiple potential outcomes causes the entire universe to, well, to branch or split.
Split into what?
Into separate, parallel, non-interacting worlds. In each of these new worlds, one of the possible outcomes is realized.
So every quantum choice creates new universes.
That's the idea. Think of it like standing at a crossroads. At every quantum decision point, every time an atom could decay or not decay, every time a particle could spin left or right, the road ahead splits. And reality takes every path simultaneously, but in different parallel universes.
Wow, okay.
Let's go back to Schrödinger's cat with MWI. When the box is opened, the universe doesn't magically collapse the cat into dead or alive. No, the entire universe, including the observer opening the box, splits into two distinct parallel branches.
Two realities forming.
Exactly. In one branch, the atom decayed, the poison was released, the cat is dead, and the version of you in that branch sees a dead cat.
Okay.
In the other branch, the atom didn't decay, the cat is alive, and a copy of you in that branch sees a live cat. Both outcomes happen. Both realities are equally real, equally valid.
They can't interact. The you that sees the live cat can't talk to the you that sees the dead cat.
Nope. That's the crucial part. Once they split, they've causally disconnected. They decohere, which we'll get to. They diverge into totally separate cosmic histories. There's no single you making the choice. Every possible outcome spawns a new reality with a version of you experiencing that outcome.
That is a lot of universes, an unimaginable number constantly splitting.
Infinitely splitting, potentially, yeah. It's a staggering concept.
Okay, so what's truly fascinating here, if you accept this premise, is how MWI explains why we only ever seem to experience one definite outcome. If both dead and alive cats exist in different branches, why do I only see one?
Good question. Where does our classical reality come from?
The explanation lies in a really important physical process called quantum decoherence. Decoherence is essentially how a quantum system loses its quantumness, its ability to show interference and superposition through interaction with its surrounding environment.
Like the quantum fuzziness gets washed out.
Exactly. Think of ripples on a perfectly still pond. If you drop two pebbles, you get beautiful interference patterns where the ripples cross. That's like quantum coherence.
Right.
But now imagine the pond is being constantly disturbed, wind, rain, vibrations. Those delicate interference patterns get completely scrambled and washed out very quickly. They decohere and become indistinguishable from the background noise. The quantum effects disappear.
So interaction with the environment destroys the quantum weirdness.
It effectively suppresses it, makes it practically unobservable on macroscopic scales. Now, within the MWI framework, this interaction with the environment, your brain interacting with the light from the cat, the air molecules bouncing off everything, the measuring device itself causes the separation of the different branches of the wave function.
Ah, so decoherence is the mechanism for the split becoming permanent.
Precisely. Yourself, your consciousness, your measuring apparatus becomes entangled with one specific outcome, for e.g., live cat. This entanglement effectively isolates your branch of reality from all the other branches where different outcomes occurred.
So the collapse we thought we saw in Copenhagen.
Isn't a real physical collapse at all, according to MWI. It's an illusion. It's just the result of our perspective being confined to a single decohered branch of this vast, ever-branching multiverse. We can no longer perceive or interact with the other branches because they've effectively become separate worlds from ours due to decoherence.
Okay, that's elegant in a way. It gets rid of the collapse problem.
It does, and that's one of its main selling points. It offers a consistent, deterministic resolution to many of those tricky quantum paradoxes, like Wigner's friend or Schrödinger's cat, because every possible outcome actually happens, just in its own branch. It also removes that awkward split between the quantum world and the classical world. In MWI, everything is quantum, including observers.
So the observer isn't special. They just get entangled and split along with everything else.
Exactly. Your consciousness, whatever that is physically, splits along with the universe at every quantum event. There are countless versions of you branching off every fraction of a second.
That's existentially challenging.
To say the least.
And some proponents, like David Deutsch, they take this even further, right? They say MWI isn't just an interpretation.
That's right. Deutsch, who's a major advocate, argues passionately that MWI is actually a full-fledged theory, or even a meta-theory. He suggests it's the only logically coherent way to make sense of quantum mechanics as it is written, without adding extra ad hoc rules like collapse.
And does he offer any evidence or arguments beyond coherence?
Well, he points to experiments like the classic double-slit experiment. Even when you send just one photon through at a time, the photon still creates an interference pattern as if it somehow went through both slits.
Right, the wave-particle duality thing.
Deutsch interprets this differently. He suggests the only way to explain that interference is if the photon in our universe is interacting with photons in other parallel universes' photons that went through the other slit in their respective worlds.
Whoa. So interference patterns as evidence of other universes interacting with ours.
That's his argument. It's a bold claim, and certainly not universal accepted, but it shows how proponents see MWI not just as an interpretation, but as having real explanatory, even potentially empirical consequences.
Okay, so just to recap the main players here in the quantum world, we've got Copenhagen.
Collapse, randomness, observer is special.
I've got de Broglie-Bohm.
No collapse, deterministic, hidden guiding waves, but non-local.
And we've got many worlds.
No collapse, deterministic, observer splits, reality branches, but requires countless universes.
They are radically different pictures of reality.
Fundamentally different. And these aren't just abstract arguments for physicists. They represent profoundly different views of your reality, how it behaves, whether it's predetermined, whether chance is real, and what your place in it might be. It cuts deep.
It absolutely does. Now, if the quantum multiverse, with its constant branching and splitting selves, felt mind-bending, well, buckle up again. We're about to shift scales dramatically.
From the very small to the very, very large.
Exactly. Let's expand our view from subatomic quantum events to the structure of space-time itself, to cosmology. Because MWI isn't the only game in town when it comes to multiverses. Other types arise from thinking about the universe's origin and evolution.
Right. These are often called cosmological multiverses, and they come from theories like inflation and string theory.
And Max Tegmark, the physicist, he actually created a useful classification system for these, didn't he? To help keep them straight.
Yes, his 4 levels of multiverses. It's a really helpful framework. We can focus mainly on the first 2 levels today, and then connect it to the idea of the string theory landscape, which ties into level 2.
Okay, sounds good. Let's start with level 1. What's the level I multiverse?
Level I is often called the quilted multiverse, and it's arguably the least controversial, maybe the simplest, of the cosmological types.
Simplest. How so?
It basically arises from just one core assumption. If space is truly infinite, and our best cosmological models right now, based on measurements of the universe's flatness, suggest it very well could be infinite.
Okay, infinite space.
Then, just purely based on probability, everything that can happen within a finite region of space must eventually happen somewhere else, infinitely far away, and it must repeat infinitely many times.
Because in infinite space, any finite arrangement has to recur.
Precisely. Think about our observable universe. Everything we can see from Earth out to the distance, light has traveled since the Big Bang. We call that our Hubble volume. It's huge, but finite. If space is infinite, then there must be an infinite number of these Hubble volumes out there, beyond our horizon, like patches in an infinite quilt, hence the name quilted multiverse.
Okay, so infinite patches identical in size to our observable universe.
Exactly. Now, the key characteristic of level I is that while these infinite other patches can have different histories, different arrangements of galaxies, different planets, maybe even different versions of you living slightly different lives,
Bro.
they are all governed by the exact same fundamental laws of physics as our own Hubble volume. Same gravity, same electromagnetism, same particles.
So same rules, just different starting conditions or random outcomes within those rules, leading to different histories in faraway patches.
Yeah, that's it. Imagine an infinitely vast tapestry. Somewhere out there, incredibly far away, there's another region of space that started out identically to ours and evolved identically. There's another you doing exactly what you're doing now. And infinitely many other regions that are slightly different or wildly different, but all following the same basic physical laws. It's just a consequence of infinity and probability.
Okay. Still mind-bending, but maybe less radical than universes splitting every second.
Perhaps. It doesn't require changes to fundamental physics, just the assumption of infinite space.
All right. So what's level 2? You said this one gets really interesting.
Yes. Here's where things get really wild, opening up possibilities that scientists are actively exploring. This is the level 2 bubble multiverse, and it's seen as a natural, almost unavoidable consequence of the theory of eternal inflation.
Eternal inflation, I've heard of that. It relates to the Big Bang.
It does. Cosmic inflation is the idea that the very early universe, just fractions of a second after the Big Bang, went through this period of incredibly rapid exponential expansion. It stretched space out enormously fast. Inflation solves a lot of problems in standard Big Bang cosmology, explaining why the universe is so flat and uniform on large scales.
Okay, so inflation happened early on. What makes it eternal?
Well, the theory of eternal inflation, developed in the 1980s by physicists like Andre Linde and Alexander Vilenkin, suggests that this rapid expansion didn't stop everywhere at the same time.
Wow.
Instead, while inflation did stop in our region of space, allowing our universe to form galaxies and stars, it continues eternally in other vast regions of space, constantly stretching and expanding exponentially.
So background is still inflating.
Exactly. The picture is like a giant, endlessly churning ocean of inflating space, and within this ocean, randomly, patches stop inflating and bubble off, forming distinct new universes like ours.
Like bubbles forming in boiling water.
That's a common analogy, yeah. A foam-like structure. The eternally inflating background keeps spawning these infinite bubble universes, each born from its own localized end-of-inflation event.
Okay, infinite bubble universes forming in an ever-expanding metaspace.
Right. And here's a crucial point. The space between these bubbles is still undergoing that super rapid, eternal inflation. It's expanding faster than the speed of light.
Faster than light.
Yes, the expansion of space itself isn't limited by the speed of light. This means the bubbles are rapidly pushed apart from each other, becoming causally disconnected. We can never reach them, never see them, never interact with them. The space between us is just expanding too fast.
Okay, so they're truly separate universes in that sense. We're isolated in our bubble.
Totally isolated. And here's the really mind-blowing part, the defining characteristic of level 2. Each of these bubble universes can potentially have different fundamental physical constants.
Wait, different laws of physics.
Potentially, yes. Or at least different values for the constants that determine how those laws operate. Things like the strength of gravity, the mass of the electron, the speed of light, the cosmological constant that governs our universe's current acceleration.
All those numbers that seem perfectly set for our universe could be different in other bubbles.
That's the prediction from eternal inflation combined with ideas like string theory, which we'll get to. Each bubble could cool down from its Big Bang with a different set of physical parameters, leading to vastly different types of universes. Some might collapse immediately, some might expand forever into cold emptiness, some might not allow atoms to form. A huge variety.
Wow.
Okay.
That's a much bigger multiverse than level 1.
Yeah.
Different physics and different bubbles.
Absolutely. It opens up a whole new realm of possibilities.
And you mentioned this connects to a major puzzle in cosmology.
Yes. If we connect this level 2 multiverse idea to the bigger picture, it offers a potentially powerful and, for many, very elegant solution to one of the deepest, most perplexing mysteries we face, the fine-tuning problem.
Oh, right. The universe seems suspiciously perfect for life.
Exactly. The fine-tuning problem is the observation that the fundamental constants of nature in our universe, these numbers like the strength of forces, particle masses, the amount of dark energy, seem to be incredibly precisely calibrated, just right, for the existence of complex structures like stars, galaxies, planets, and ultimately, life itself.
It's like the universe is a giant machine with dozens of dials, and they all just happen to be set to the exact values needed for us to be here.
That's a great way to put it, and the degree of precision is often staggering. If you were to change the value on some of those dials by just a tiny fraction, sometimes 1 part in a million, sometimes much, much less,
What would happen?
disaster. The universe would likely be completely barren and lifeless, stars might never ignite, or they might burn out instantly, atoms might not be stable. Complex chemistry, the basis for biology, would be impossible. Gravity might be too weak to form galaxies or too strong, causing everything to collapse back immediately.
So it really looks like an unbelievable cosmic coincidence that we ended up with the exact right settings, almost like it was designed.
That's certainly how it appears at first glance. It feels incredibly improbable that these constants would just randomly fall into the tiny life-permitting range out of all the possible values they could have taken. This leads to that profound question: is it just dumb luck? Is it evidence of a designer? Or is there another explanation?
And the level 2 multiverse is that other explanation.
It provides a compelling one, yes, especially when you combine eternal inflation with ideas from string theory, specifically the concept of the string theory landscape.
Okay, string theory. Tiny vibrating strings instead of point particles, extra dimensions. How does that fit in?
Right. String theory is our leading candidate for a theory of everything, aiming to unify quantum mechanics and general relativity. At its core, it suggests that fundamental particles are tiny vibrating strings. And, importantly, it requires more spatial dimensions than the 3 we see, usually 10 or 11 in total.
Where are the extra dimensions?
They're thought to be compactified, curled up into incredibly tiny, complex shapes, far too small for us to perceive directly. Now, a landscape is a metaphor. Imagine a vast, multi-dimensional, mountain range representing all the possible ways those extra dimensions could be curled up.
Okay, a landscape of possible geometries for the extra dimension.
Exactly. And each valley or minimum point in this landscape corresponds to a possible stable vacuum state, a way the universe could be, according to string theory.
Like different possible ground states for the universe.
Precisely. And here's the key insight. Each of these different stable vacuum states, each valley in the landscape, corresponds to a universe with a unique set of effective physical laws and constants.
Ah, so the way the extra dimensions are curled up determines the physics we see in our dimensions.
That's the idea. Different shapes for the extra dimensions lead to different ways the strings can vibrate, which in turn determine the masses of particles, the strengths of forces, the value of the cosmological constant, all those fine-tuned parameters.
And how many possible valleys are there in this landscape? How many possible sets of laws?
The estimates are astronomical. Literally, something like 10 to the power of 500 possible stable vacuum states.
10 with 500 zeros after it.
Yes, an unimaginably huge number of distinct possible universes, each with its own unique physics, all mathematically allowed by string theory.
So if eternal inflation creates infinite bubble universes, level 2, and the string landscape provides a vast menu of possible physics.
Then you put them together. Eternal inflation could naturally populate the string landscape. Each bubble universe that forms could randomly land in one of those 100 and 500 valleys, inheriting that specific set of physical laws and constants.
So the multiverse would contain bubbles with virtually every possible type of physics allowed by string theory.
That's the picture, a vast cosmic playground where every possibility is realized somewhere. And this brings us right back to fine-tuning and how the anthropic principle fits in. It raises that important question. What does this cosmic lottery mean for us?
The anthropic principle. Like, that's the idea that we see the universe the way it is, because if it were different, we wouldn't be here to see it, right?
In its simplest form, yes, it's a selection effect. We must find ourselves in a universe whose properties allow for observers to exist, simply because observers can only exist in such universes.
It sounds almost tautological, but
But in the context of a multiverse, it gains real power. If there really is this vast ensemble of universes out there, maybe infinite-level eye patches or infinite-level 2 bubbles, exploring the 10,500 string landscape possibilities where essentially every possibility happens.
then it's no longer surprising that some universes have the right conditions for life.
Exactly. Our existence in one of them becomes not a miracle-demanding explanation, but simply an inevitable outcome of a vast cosmic lottery. We find ourselves in a universe with fine-tuned constants for the same reason you find yourself on Earth rather than Jupiter. It's the only place nearby where you could exist.
So it flips the problem.
Yeah.
Instead of asking, why is our universe so incredibly fine-tuned, we ask,
Why do we find ourselves in one of the universes from the multiverse that is fine-tuned? And the answer is simply because we couldn't exist anywhere else.
It changes the paradigm completely. It removes the appearance of cosmic coincidence or design and replaces it with statistics and observation selection effects within a much larger reality.
Precisely. It transforms what looks like incredible luck into an expected outcome, given a large enough number of trials, in this case, universes. And that conceptual shift, that potential resolution of the fine-tuning problem, is arguably the multiverse's most powerful argument, especially for the level 2 string landscape scenario.
That is a really compelling reframe of that huge cosmic mystery. Okay, so we've explored how the multiverse idea pops up from both quantum mechanics trying to solve the measurement problem and from cosmology and string theory trying to explain cosmic evolution and fine-tuning. These are elegant, if definitely mind-bending solutions.
They offer potentially powerful explanations for deep puzzles.
But let's be really clear. This is not universally accepted science. Not even close, right? So what does this all mean for whether we can even call this stuff science in the first place?
You've hit on the absolute core of the controversy. The central debate swirling around the multiverse isn't usually about its internal mathematical logic, often that's quite sound within the specific theoretical framework. The real fight is about its scientific legitimacy. Is it testable? Is it science? Or just philosophy?
Right. And the main argument from the critics, you hear names like George Ellis, Sabine Hossenfelder mentioned often. What's their core objection?
Their main point is clear and direct. The multiverse, particularly the cosmological kind where other universes are causally disconnected, is essentially a philosophical notion, or metaphysics. It's not a testable scientific hypothesis because it cannot be empirically falsified.
Falsified, meaning you can't prove it wrong.
Exactly. They argue that if a theory, no matter how elegant or how much explanatory power it seems to have, cannot, even in principle, be disproven by some conceivable observation or experiment, then it steps outside the proper domain of science.
It becomes like a matter of faith or just speculation.
That's the concern, that it moves into the realm of untestable belief, rather than knowledge grounded in empirical evidence. And what's fascinating here is how this whole debate really connects back to fundamental ideas about what science is, particularly those articulated by the famous philosopher of science, Karl Popper.
Popper and falsifiability. That rings a bell from philosophy class.
Right. Popper's principle of falsifiability is a cornerstone of 20th century philosophy of science. He argued that for a theory to be genuinely scientific, it must be potentially disprovable. There has to be some imaginable observation that could show the theory is wrong. If no observation could ever contradict it, then it's not making risky testable predictions. It's not really science.
Like saying all swans are white. That's falsifiable because finding one black swan proves it wrong.
Precisely. But if you say invisible, undetectable unicorns exist, how could you ever prove that wrong? It's unfalsifiable.
Okay, so how do critics apply this to the multiverse?
They argue pretty forcefully that because the predicted other universes, especially the level 2 bubble universes or the MWI branches, are, by definition, causally disconnected from us and unobservable, well, then the theory makes no testable predictions about them. We can't go visit them. We can't receive signals from them.
So no observation could ever prove they don't exist.
Exactly. George Ellis puts it very bluntly. The lack of any causal connection in such multiverses really places them beyond any scientific support. You simply can't test the core claim.
And there was another criticism mentioned, the inverse gambler's fallacy.
Yes, the philosopher Philip Goff brings this up specifically regarding using the multiverse to explain fine-tuning. He argues it's like seeing someone roll snake eyes, 2 ones, on dice, and concluding, wow, that's rare. They must have been rolling the dice for ages to finally get that result.
But that doesn't follow logically. The past rolls don't influence the current one.
Right. Goff argues that inferring a multiverse, many past rolls or universes, just because our universe looks rare or fine-tuned, is a similar kind of fallacy. It's making an untestable assumption, the existence of other universes, to explain something improbable in our own without independent evidence for those other universes. Critics see it as an intellectual sleight of hand.
Okay, that's a strong critique. It puts the multiverse outside of traditional science based on testability. How do the proponents respond? Is falsifiability the be-all and end-all?
That's exactly their counterargument. They push back and say, okay, while falsifiability is obviously important, maybe it's not the only criterion for what makes a theory scientific, especially when we're pushing the boundaries of knowledge.
What else matters then?
They argue that other qualities like simplicity, explanatory power, internal consistency, elegance, these also play a crucial role in evaluating scientific theories. Does the theory solve more problems than it creates? Does it unify disparate concepts?
And they feel the multiverse does that.
Yes. They argue the multiverse isn't some weird ad hoc addition just tacked on to solve fine-tuning or the measurement problem. Instead, they see it as a non-optional prediction that naturally, even inevitably, emerges from our best existing theories. Theories like quantum mechanics and Everett's formulation, inflationary cosmology, and string theory.
So the argument is, if you accept inflation or string theory or the Schrödinger equation without collapse, then you have to accept the multiverse. It comes as part of the package.
That's the core idea for many proponents. Physicist Sean Carroll, for example, argues that the multiverse does have explanatory power for things we do observe, like the properties of the CMB or the values of constants. And he suggests our confidence, our credence in the multiverse, can still go up or down based on future observations and improvements in our understanding of those parent theories.
So even if we can't directly test the multiverse, we can test the theories that predict it.
Exactly. If future experiments provide stronger support for eternal inflation, or if string theory makes successful, testable predictions in other areas, like particle physics, then our confidence in their consequence, the multiverse, should also increase, even without direct proof. It becomes plausible by association with successful parent theories.
That's a different way of thinking about scientific support, indirect validation.
It is. It shifts the focus from direct falsification of the multiverse itself to the ongoing testing and validation of the broader theoretical frameworks it stems from.
Okay, but are scientists just relying on theoretical arguments? Are there any attempts to find actual empirical evidence, however indirect?
Oh, absolutely. If we connect this to the bigger picture, the hunt for any kind of empirical evidence, even circumstantial, is where science really tries to bridge that gap between theory and reality. Despite the challenges, scientists are actively looking for potential indirect signatures of other universes within our own observable universe.
Signatures, like echoes or footprints left behind.
Kind of, yeah. One of the main places they're looking is the cosmic microwave background, the CMB.
Right, that afterglow from the Big Bang. The oldest light in the universe.
Exactly. It's like a snapshot of the universe when it was just 380,000 years old. It contains a wealth of information about the early universe's conditions and structure.
So what kind of signature might another universe leave in the CMB?
Well, theoretically, if our bubble universe ever collided or interacted with another bubble universe during the early stages of eternal inflation,
A cosmic bump?
you could think of it like that. Theory predicts these collisions might have left specific patterns, perhaps large circular imprints or bruises, in the temperature map of the CMB. These would look like regions with slightly different temperatures or polarization properties than expected from the standard random fluctuations of the Big Bang.
Have we seen anything like that?
There was some excitement around 2010. Some initial analyses of data from the WMAP satellite did seem to show a few potentially anomalous cold spots or other features that some researchers tentatively interpreted as possible evidence for bubble collisions.
Wow, so potential evidence.
Potential, but highly tentative. Science is all about cross-checking and getting better data, and unfortunately, a more thorough analysis using the later, higher resolution data from the Planck satellite, well, it did not confirm those findings.
So the better data didn't support the collision idea.
The Planck team looked very carefully and found no statistically significant evidence for these specific bubble collision signatures or for other predicted effects like gravitational pulls from nearby universes. That doesn't definitively rule out the multiverse. Of course, maybe collisions are rarer or leave fainter signals, but it means that specific hoped-for piece of evidence hasn't materialized in our best data so far.
Any other potential clues being investigated?
There are other, even more speculative ideas. You might have heard about Rangaram Turi's claim a few years ago about a different kind of anomaly in the CMB, which he speculated could potentially be caused by a neighboring universe dumping baryonic matter, normal matter, into ours early on.
Dumping matter, like cosmic trash disposal.
Something like that. But even Turi himself was extremely cautious, emphasizing that it was highly speculative and required much more investigation. He explicitly stated, Unusual claims like evidence for alternate universes require a very high burden of proof.
So still very much in the realm of speculation, not confirmed evidence.
Very much so. But it illustrates the key point. Even without being able to directly observe other universes, scientists are rigorously pursuing every possible indirect clue they can think of using our most precise instruments like the CMB satellites. It shows the dedication of scientific inquiry, pushing the boundaries even when the challenges seem immense, perhaps even insurmountable.
Okay, so this whole debate, falsifiability versus explanatory power, the search for indirect evidence, it really highlights how frontier science bumps up against philosophy, doesn't it?
Absolutely. It's a perfect example. The multiverse discussion forces us to grapple with fundamental philosophical questions, like the demarcation problem that philosophers of science talk about.
Demarcation, meaning drawing the line.
Yeah, how do we draw the line between what counts as legitimate science and what's merely interesting speculation or metaphysics or even pseudoscience? Where does theory become untestable philosophy?
And the multiverse seems to sit right on that boundary line for many people.
It really does. It forces us to ask, what counts as evidence when direct observation is impossible by definition? How much explanatory power does a theory need to have before we take it seriously, even if it's not directly falsifiable in Popper's strictest sense?
It's clearly not a simple dispute about interpreting data points. It's a much deeper conversation.
It's a deep, ongoing, and fundamentally unresolved discussion about the limits of our knowledge, the reach of our series, and the very nature of scientific methodology itself when we probe the ultimate nature of reality. The multiverse holds up a mirror to science, asking us about its own boundaries and capabilities. #tag outro. So summing up this incredible journey, what's fascinating here is that the multiverse, in its various guises, quantum and cosmological, really stands as a testament to the sheer ingenuity and the boundless imagination of modern theoretical physics.
It's come a long way from the ancient Greeks.
Oh, absolutely. It's this profound idea that arises quite naturally, almost inevitably, from our most successful, most trusted physical theories, quantum mechanics, inflation, string theory. But at the same time, it presents an equally profound challenge. It truly feels like a concept with a dual nature. Immense power, but also profound peril, scientifically speaking.
Okay, let's break that down. Where does its power lie?
Its power, I think, lies primarily in its ability to offer these incredibly elegant, often deterministic solutions to some of the deepest, most persistent paradoxes we face. In quantum mechanics, MWI offers a way out of the measurement problem without invoking that mysterious, unexplained collapse. It takes the Schrödinger equation at face value.
Just lets the universe branch.
Right. And on the cosmic scale, the level 2 multiverse, especially combined with the string landscape, provides arguably the most compelling explanation we currently have for that seemingly miraculous fine-tuning of our cosmos. Why is our universe just right for life? The multiverse answer, because all possibilities exist, and we're just in one that works, has a powerful elegance to it. That's its biggest draw, perhaps.
Solving deep problems elegantly. That's appealing. But what about the peril, the challenges?
The main peril, the biggest challenge, isn't really technical within the mathematics itself, which is often quite rigorous. The danger is primarily philosophical, or maybe methodological. It comes back to that central issue we discussed, its pervasive lack of empirical falsifiability, especially for the cosmological multiverses.
That cornerstone of the scientific method.
Exactly. While proponents argue, quite persuasively sometimes, that it's a non-optional prediction of otherwise testable parent theories, the hard fact remains. We currently have no statistically significant direct observational evidence for other universes. Those hoped-for signatures in the CMB haven't panned out so far.
So it remained unproven, possibly unprovable.
And that's the philosophical peril. Does it risk undermining the empirical foundation of science if we embrace theories whose core predictions might be forever beyond observation? It forces us to confront the very boundaries of what we can scientifically know, and maybe even pushes us to reconsider what counts as scientific validation itself.
So what does this all mean for you, listening to this? As we think about the future of science and our understanding of reality, where do we go from here with the multiverse?
Well, the major hurdle, as we just said, is that lack of clear, unambiguous observational evidence. No smoking gun in the CMB, no definitive cosmic bruise detected, at least not yet. So the path forward for the multiverse idea probably won't involve some sudden, single, definitive observation that proves it right or wrong. That might never be possible, especially for the cosmological versions.
So how will its status change?
Its fate seems likely tied to the continued testing and refinement of the foundational theories from which it emerges. quantum mechanics, inflationary cosmology, string theory.
The parent theories?
Exactly. As our understanding of these core theories deepens, as we test them in new ways, maybe through particle accelerators, gravitational wave detectors, future cosmological surveys, the plausibility of their multiverse predictions will either rise or fall with them.
So if, say, string theory makes a correct prediction about particle masses that we then discover.
That would indirectly boost confidence in its other predictions, including the landscape and the multiverse. Conversely, if inflation theory runs into serious trouble, or if a completely different theory of quantum gravity emerges that doesn't predict a multiverse,
Then support for the multiverse idea would likely wane.
precisely. Its fate is intertwined with the fate of its theoretical parents. Ultimately, the quest for the multiverse is really part of a larger quest for a more complete, unified theory of reality. It's a journey that forces us to constantly reconsider our place in the cosmos and the ultimate limits of our scientific understanding. It's pushing science itself into new territory.
It really is. And thinking about MWI in particular, this raises a really profound, almost personal question for you to ponder. Something that goes way beyond the physics and into philosophy, maybe even spirituality. If our universe truly is just one of an infinite number of possibilities, if every single quantum choice, every coin flip, every radioactive decay causes reality to branch, creating new universes and new versions of yourself, what does that actually mean for your sense of free will?
If every choice you could make is made by some version of you in some branch,
Yeah. Does you choosing porridge instead of toast this morning really mean anything if another you in a parallel world chose the toast? And what does it mean for the very concept of your individual existence, your unique identity, if there are infinite versions of you out there making every conceivable choice, living out every possible life path? Some identical, some slightly different, some wildly different. Where's the real you in all of that?
it's a dizzying thought. What makes your branch, your choices special?
Exactly. Something to really chew on. Thank you so much for joining us on this incredibly deep dive into the quantum and cosmic enigmas of the multiverse. It has definitely been a mind-bending journey.
It always is with this topic.
We hope it's given you plenty to think about until next time on The Deep Dive.